Hey there, welcome back to Short Takes 331. Today we're going to talk about the binomial theorem and how to prove it. So let's get started. So this is a statement of the binomial theorem. A plus b to the nth power is the sum from k equals 0 to n of the binomial coefficient nk, which is simply this n factorial divided by k factorial n minus k factorial, times a to the k, b to the n minus k. Now, of course, you can flip a and b here. You can say b plus a, and it's the same result. So you can change here b and a as well. So you get to choose which one you go to the kth power and which one gets to have the n minus k power. And sometimes it's convenient to choose a or b, so which one you pick depending just on convenience. So the way to prove this is by induction. That's the simplest way I know. And the idea of induction is sort of like this. So first you prove for a low number. In this case, we can easily prove it for n equals 1. So we're going to check it out. And then you proceed to prove that the case of order n implies the next one. And so once you have that, then basically it's like pulling from a string. And the axioms, if you want, of induction tell you that this is valid for arbitrary n, at least arbitrary finite n. So in this case, then n equals 1, you have a plus b to the first power, which is of course a plus b. And let's see if it takes the form of this sum that we proposed here. So the sum will go from k equals 0 to 1. We'll have the binomial coefficient 1k, a to the k, b to the 1 minus k. And what is this? Well, the first term is k equals 0, and we have the binomial coefficient 1, 0, a to the 0, b to the 1, and so that's b. And the binomial coefficient 1, 0 is just 1. And then we have the second term is the term with k equals 1, and so it's 1, 1 for the binomial coefficient, a to the 1, b to the 1 minus 1, which is 0. And so we have binomial coefficient 1, 1, which is just 1, times a. And so this is b plus a. And so, of course, this is totally fine. It's a little trivial, but that's okay. We go through the formalities. And so we have n equals 1. And so now we're going to prove that if we assume the case of order n to be valid, so the power n to really be equal to this sum. So if we assume that the theorem is valid for a particular value n, that it implies the next order, the n plus 1. And so if we do that, and we have the first case, then like I said, it's like pulling from a string, at least that's the idea. And so it will be valid for arbitrary n. And so, and of course we're assuming here always that n is an integer. And so that's the way this proof goes. And so a plus b to the n plus 1 power is something we can always write as n plus b to the nth power times a plus b. Now this helps us because then we know the result for a plus b to the power n. And this is always how it goes with induction proofs. You assume the nth level or nth order result, and then you have to make it appear somehow in the n plus 1th order. And so this is how we play this game. We say then a plus b to the n plus 1 is a plus b to the n times a plus b. And so we separate this now into two terms, one for the a and one for the b here, because we know what a plus b to the power n is. This is this finite sum where I've added a 1 to a to the k. So this a to the k now is a to the k plus 1 because of this a. And over here, we have the same sum, but b to the n minus k plus 1. And this plus 1 is because this is second term b here. So now what we're going to do is, first of all, I'm going to relabel this index k in this sum, and I'm going to shift it by 1. And so I'm going to make it start at 1 and go to n plus 1. If you want, you can rename it k prime. I just use k again. It's the same sum if I go from k equals 1 to n plus 1. If I shift everywhere else k by minus 1. And so this k becomes k minus 1. This k plus 1 becomes just k. And this minus k here becomes minus k plus 1. And so now I have this sum entirely in terms of a variable that starts at 1 and ends at n plus 1. And this one I haven't touched at all. This one I leave it as it is. So why would I want to do this? The main reason I want to do this is that I want to make sure that this object looks just like this object. And why do I do that? Well, you see over here, when I have a to the k, b to the n minus k, for a n plus 1 case, this would look like a to the k, b to the n plus 1 minus k. And that's exactly what we have here. N minus k plus 1, n minus k plus 1 is exactly the type of term that I would have for the n plus 1 case. And so I want that to appear. And so I know where I'm going. So I manipulate the formulas to make that appear explicitly, and then I see what results from that. And so I do that. And the next thing I do is I separate the n+1 term from this sum, and the n+1 term from this sum will be, if you look carefully, let's see, the n+1 term. When k is n+1, I have nn here, which is just 1. I have a to the n+1, and I have b to the 0th power. So n minus n+1 plus 1, that will give you the 0th power. And so it's this term here, a n+1. So the last term here is just n plus a to the n+1. And so I separated that term. And over here, I'm going to separate the k equals 1 term. And you can see that the k equals 0 term. The k equals 0 term, and you can see that the k equals 0 term is actually b to the n+1. There's a to the 0, n 0 here, so it's this term here. So once again, I look at this result that I got so far, and I separate the n+1 term from the sum, and I put it over here. And on this one, I separate the k equals 0 term, and I put it over here. Why do I do that? Because these two sums are very, very similar, except that they differ in that this has this extra term at the end, and this is the extra term at the beginning. This one goes from n to n+1, this one from 0 to n, and so this one has an extra term at the end, this one has an extra term at the beginning. I separate those two. And once I separated those two, I can write this whole expression into this sum plus these two terms. And this sum then goes from 1 to n. That's all the stuff that these two have in common. It goes from 1 to n. I have nk minus 1, nk for the binomial coefficients that I sum together, and then I have a to the k and b to the n+1 minus k from here and from here. I get the same coefficients, the same factors here and here with all the right powers. And so now we're getting closer to the result that we want. We want this sum to go from 0 to n+1, so we're going to look into that, and it's going to end up being that exactly these two terms are the terms that we need. But first we have to manipulate the sum of these two binomial coefficients. If I write them explicitly, these two binomial coefficients look like this. I can write the n minus k plus 1 factorial as n minus k plus 1 times n minus k factorial, because this is one more than n minus k. So it's n minus k plus 1. So then the factorial of n minus k plus 1 is n minus k plus 1 times n minus k factorial. And I can play the same game with k times k minus 1 factorial. And the reason why I manipulate this in this way is simply to simplify my calculations and do the sum of these two fractions. So in other words, this two things really is just summing these fractions. And if you do it carefully, you find that you end up with this result. So if you follow this chain of identities here, which is actually pretty short, you'll find that doing the sum, you end up with n plus 1 factorial divided by k factorial, n plus 1 minus k factorial. And that's the n plus 1k binomial coefficient. In other words, this object here is exactly what we need. It's the n plus 1k factorial binomial coefficient. So remember, over here, the binomial coefficient that we have in our in the result that we want is nk. So the n plus 1 case would say n plus 1k. And that's exactly what we're getting down here when we sum these two terms. We get n plus 1k. And so far what we have then is this. We have shown that a plus b to the n plus 1 power is the sum from k equals 1 to n of n plus 1 k binomial coefficient, a to the power k, b to the n plus 1 minus k. And now if you put k equals 0, you see that you recover b to the n plus 1. It's very easy to see. If you imagine putting k equals 0 here, you're going to get 1, you're going to get a to the 0, and you're going to get b to the n plus 1. So that's this guy. And if you put k to n plus 1, so if you were to add one more term here to the sum at the end, you get a to the power n plus 1. You can easily convince yourselves that that's true. And so now we can incorporate these two terms that we separated before into the sum, one at the beginning and one at the end. And so we're then allowed to say that a plus b to the power n plus 1 is k equals 0. It's the sum from k equals 0 to n plus 1 of the n plus 1k binomial coefficient, a to the k, b to the n plus 1 minus k. And that's it. That's the result. And we have then proven that by assuming that the nth order case is true, then we can prove that the same holds for the n plus 1 case. We use that result. We use the nth order result to prove the n plus 1 order result. We prove the n equals 1 result, and so we've satisfied then all the conditions to prove that the binomial expansion or the binomial theorem is valid for arbitrary n. So that's the end of the theorem, the end of the induction proof. And now I'm just going to make a few remarks. So I want to point out that usually when you have a long list or a long list of factors like this, one after the other, n times, a plus b times a plus b and so on, n times, you can think about this intuitively. So, for example, how many ways do I have to get the nth power for a? Well, every time you multiply, you're going to pick one factor from each of these, or rather one term from each of these factors. So I can pick an a here and an a here, and then maybe a b and maybe another a. But if I want to end up with a to the nth power, then there's only one way to do it. I have to pick the a here and the a here and the a in each guy, because I only have n factors. And so I can only do that in one way. And so this means that a to the n will appear only one time. And that's why the coefficient of a to the maximum power available here, in this case n plus 1, is just 1. Okay, so imagine that that's exactly what you would get if you have n plus 1 factors. Here the example is with n factors. So what about n minus 1, a to the n minus 1b? That's the next thing that could happen. Well, there's only n times that you can do this, n ways to do this. How is that? Well, that's also easy to see. So in how many ways can you pick a to the nth power, so n minus 1 powers of a, so and 1 power of b? Well, you have to pick a everywhere, basically, except at one point, one factor which you can pick a b. So let's say we start with picking a b here and then a everywhere else, or then a and then b and then a everywhere else. So you see, for each factor, you can only pick b once if you are to end with this result. And there's n ways to do that. There's only n ways to do that. You can pick b here, or on the next one, and so on, or on the last one. And so that will give you then a to the n minus 1 times b. So there's only n ways to do that. And you can continue to play this game and see, well, how many ways are there to choose 2 b's or 3 b's and so on, until you get to the end, where you say, how many ways are there to pick the maximum value, the maximum number of possible b's that I could pick from here? Well, the maximum number of b's that you could pick is, of course, n. And the only way to do that is to pick b here and b here and b here and b all the way at the end. And that's just b to the n. And there's only one way to do that. And so this is why there's this sort of symmetry between the factors, the binomial coefficients at the beginning and at the end. So there's a 1 and then an n, and then at the end there's an n and then a 1. And if you're interested in exploring that symmetry a little bit more for various powers of n, you should check out something called Tartaglia's triangle. You can look that up and do a bit of research, and you'll find more about that. So that's just a comment on how to think intuitively about stuff that involves multiple factors with multiple terms inside of them. A lot of the time in physics, we find ourselves working with expressions of this form, 1 plus x to the n, or 1 plus something to the n. I guess this x could be a function, it could be anything in principle. It doesn't have to be a variable. It could be just any kind of object. It could be even a matrix in some cases. So 1 plus x to the n, then according to our binomial theorem, let's see, where do we have the nth order? Up here, according to our binomial theorem, suppose a is 1 and b is x, then you get to pick what is a and what is b. So if you pick the n minus k to be applied to the 1, then you end up with this simple expression. So 1 plus x to the power n is just the sum from k equals 0 to n of the nk binomial coefficient, sometimes called n choose k, and x to the kth power. So this is a simple formula that you can expect to see a lot of the time for 1 plus x to the power n. And it's easy to see then that for k equals 0, or the first couple of terms rather, is k equals 0, k equals 1. And so for k equals 0, you get just x to the 0, and so that's 1. So this formula starts with a 1. And for k equals 1, the next order over, you have n choose 1, and that's just n, and then x. So the lowest order expansion for 1 plus x to the power n is 1 plus nx, which is also something you might know from other contexts. Finally, a lot of the time in physics, we write a plus b to the n by pulling out an a to the n factor artificially. So we pull that a to the n and we pay this a down here. So we separate an a to the n, and then we write the remainder as 1 plus b over a to the power n, the whole thing to the power n. So that's a to the n, and then you can apply the binomial expansion here. And this is interesting because then the binomial expansion, this binomial theorem, tells us that 1 plus b over a to the n is just the sum from k equals 0 to n, the n choose k coefficient, and then b to the power k and a to the power minus k, because we have a here in the denominator. So this is interesting. It's also a nice and symmetric way to remember. So if you have a plus b to the power n, just pull a in front to the power n, and the rest is just n choose k, the nk binomial coefficient, that is, and then b to the power k and a to the power minus k. And you can choose what you call a or b. The one that has a minus sign is the one that is out here in front with the power n. And that's it. That's all I have for you today. I hope you enjoyed this video. If you did, please consider liking and subscribing to the channel. And as always, if you're looking for a tutor in physics or math in English or in Spanish, you can contact me at shorttakes331@gmail.com, or you can leave a message in the comment section below and I will get back to you. Finally, if you're interested in downloading the notes that appear in all of these videos, you can find them in the description. There's a link to my website, and there you can download all of this for free in PDF format. And that's it. I will see you next time.